Okay, thank you very much. Can you hear me well, Andre?
Yes, perfect.
Okay. The university invested in some very nice microphones for recording all our lectures, so I hope it's coming across well.
Yes.
So thank you very much for having me today. It's a great pleasure to be here. This is the title of my talk, Synergies of AI and Digital Twinning Construction. I've been putting a bit of thoughts around this recently, not necessarily of groundbreaking stuff, but somewhat related to the things we do here. But I will only refer a little bit to some of our work. Actually, I will refer to a number of people's work, and some of them were actually presenting during this event. The first thing I'll do, there you go, is that I'll show you a little bit of statistics about automation, well, extracted from automation construction. It's certainly not the only source of information for this information, but I think it's a good area or a good place to look because it is a journal that is really directly connected to the subjects of digital twinning and AI. Some areas are much more computer science focused, some might be very construction focused, and this is really in between. Just to give you an idea, first of all, of the whole area of automation construction, this is the number of papers that have been published in automation construction over the last 15 years. And you can see how this is growing steadily and actually increasingly. You look at the 2021 year, by April, we already had nearly 200 papers published. So it looks like we are going to explode the previous record. And it does, what it shows is that, I mean, at least it shows two things. First of all, there is a growing pool of researchers around the world and very active researchers. So, you see increase in many, if not most journals. But in my opinion, it also shows that this field, automation construction, has really expanded a lot, especially in the last 10 years, let's say 5 to 10 years. And this is actually the impact factor for the journal. So I think it also demonstrates that not only people publish a lot, but the work they publish here has an impact. And I don't mean it just to show off the journal, but just to say that there is broader and broader interest in this area. I think that's what matters. And we are kind of in this virtuous circle of interest and good quality publication, etc. Now, if you look at what is published in automation construction, I think there are some really interesting things that can be looked at. I've done some, I wouldn't say back of the envelope, but quick Excel spreadsheet analysis from data extracted about the journal. And I've been looking for words like BIM and digital twinning in the publications over the last 15 years. And you can see now that about a quarter of all the published papers refer to BIM or digital twinning in their abstract or in their title or their keywords. And among this, you can see at the bottom, the digital twinning. So this is very recent, but you can see it's starting to take off. Okay, in fact, it's probably replacing a bit of the digital twinning, building information modeling terminology. But overall, 25% is really, really significant. And now you can see what is AI. So let me clarify. When I say AI here, I think I've been looking for machine learning, deep learning technology, convolutional neural network, CNN, this kind of terminology. It doesn't cover the whole of AI, but modern AI, let's say, especially supervised learning methods. And you can see how since 2015, the number of papers that use AI has just shot up. And now we are at 25% of all our publications use or make reference to AI, at least in their title, abstract, or keywords. And within this, there is an area that has been quite buoyant, is the using AI for crack detection. In fact, Eleni just before me did refer to this type of research. And themselves alone, they represent 3% of our publications. And that has been growing. So I think that's quite insightful. And now if you look at AI and BIM and you look at combining them, then you can see that now about 4% of our publications in their abstract titles or keywords, they collectively make reference to BIM, DT, or BIM or DT, and then AI terminology. So, all this is really, really hot area and growing quickly. Automation construction is about many other things, and you can see some trends here. If you look for robot or robotic, you get a pretty flat trend actually since over the last 15 years. 3D printing, an area that is of increasing interest, is growing slowly. Drone, if you look for that, it's also growing slowly, but you can see how AI and BIM DT are really well above that. Okay, so I hope you find that interesting. I personally found that interesting. As an associate editor of the journal, I had an implicit knowledge of this, but I was keen to actually explore this more quantitatively, and I think it's really interesting. Now let's go to digital twinning. What is digital twinning? People who have covered this already in their presentations may have already provided some definitions. There is no clear, broad understanding about what is a good definition of digital twinning. In fact, there is a center that is highly referred to these days called CDBB in Britain, Center for Digital Build Britain. And if you look at two of their publications, one is the Digital Twin Hub, and the other one, can't remember, so another one of their publications, they actually give you two different definitions. And in fact, the first one is a realistic digital representation of assets, processes, or systems in the built or natural environment. And the second one is a bit longer. It gives more purpose to it. So it explains that it's used to make decisions that will affect the physical asset, but also that any changes to the physical asset should be reflected in the digital twin. And therefore, I think a good definition should probably be combining those two. I think what I like about the first one is that it makes references to the assets. And a lot of people think about digital twinning in the concept of, in the contexts of asset monitoring. But actually, processes are also an important area where digital twinning applies, and I'll show you an example later. And another thing that is really important that is not captured in the first definition is that the information has to loop around. So you also need to capture changes in the physical asset and reflect them digital twinning. And arguably, a lot of stuff that, for example, Eleni presented before me is about that or supports that. And another thing that is relevant to the discussion of digital twinning is actually Industry 4.0. So how does that, the two are certainly related and often referred to collectively, but the key aspect of Industry 4.0 is this idea that there is a need to combine, well, they often refer to IoT, AI, and robotics as core to Industry 4.0, but more broadly than just these three buzzwords, really the idea is that, in order to support digital twinning, we need to have sensors, we need to process the data, and we need to use that data to act on the physical environment. And that could be through any sort of actuators, including robotics type of actuators. And so what I will do now is I will go through a few examples of some of these. So sometimes combining one or two circles, just one circle, but I will make reflections on this, and I will particularly highlight where the AI bit, which I capture more broadly under data science, but the AI bit is increasingly relevant and used. I'll start in a broad category here. there is this report from McKinsey that was published actually back in 2016 already, which was exploring the use cases of digital twins for the construction industry, and in particularly delivering capital projects. Okay, and I find that's really interesting because this is not a use of digital twinning for asset monitoring. It's a use of digital twinning for process monitoring and process enhancement. And here you can see they have 8 categories, and under these categories they have different type of use cases. And I highlighted a number of them that for me are, can clearly benefit from the use of AI. So creating, assigning, and prioritizing tasks in real time, track progress online. To do this, you need to capture data and you need to somehow infer progress on that data. And that's not necessarily an easy task. There's a lot of uncertainty, a lot of fuzziness, and machine learning can help address this problem. Use cases for materials management, crew tracking, which to some extent is used for tracking progress, for quality control, and again, performance management. There is more about monitoring progress and performance across teams here. So there's a number of applications, and I'm sure some of you might raise your hands and say, well, actually that bullet here in the other column, you could also use AI, probably. But these are, probably half of the bullets here have obvious use of AI to support digital twin based process. In fact, we have an EU project that just started recently that aims to do more or less some of these things, where we aim to have a number of sensing solutions deployed on construction sites that we analyze, including using various type of AI type solutions. And we use that information to improve the way project managers and site managers and different types of actors on site make decisions to improve construction processes. And as many of you will know, we really need to improve, especially the predictability of construction. So it's not so much, there's a big argument that construction could be cheaper, and I'm sure we can certainly be cheaper also using these type of solutions. But I think probably the most frustrating thing in the sector is not so much the cost, but the lack of predictability. Because that's really ruins a lot of business processes, business decisions subsequently. Sorry, my slide was slow. So now I'll talk a little bit about 2 applications that broadly fit within the framework I just discussed. One is Scan-to-BIM, and the other one is Scan-vs-BIM, and I'll explain what this is about. But both of them rely on the fact that we have had this explosion in capability in terms of acquiring 3D imaging data from any sort of environment. But that is particularly useful for capturing data by the built environment, whether it is an operating asset or a building under construction or else. And here I have videos I don't play today, but on the left-hand side, you have essentially laser scanning based solutions. And here we have a scanner at the bottom mounted on the Spot robot that we are going to play with here at the university as well. And on the right-hand side, more drone-based solutions. In fact, many of you may have seen the presentation from Mani at the beginning of this symposium, and this is actually the company Reconstruct that is involved in, and that is based on his research actually, and is doing excellent work by using this type of data. And so the idea of Scan-to-BIM is that, well, in order to be able to benefit from semantically rich models for operating or renovating, refurbishing the built environment, we need to create those models in the first place. And for most of the built environment, we don't have these models. and we need to create them. So the process of creating those models needs to rely on, well, yes, how should I say? Is based on the acquisition of 3D geometry. It's certainly not the only information you need, but this is a very important step in the process. And when you look at the literature on Scan-to-BIM, you can see how things have evolved and how slowly modern AI techniques are attacking the problem. So this is just for the general audience to explain, what is the idea here is that we start at the top left with a point cloud model. And at the end, at the bottom right, we need to have a 3D volumetric and semantically rich model. And to go there, you go through different stages. And here we show the typical stages. They don't have to be exactly in that order, exactly perform like this, but typically people look for floors. Once they have floors, they look for the rooms or spaces, and then they start modeling those by finding the boundaries, modeling the walls, then finding openings like windows and doors, and slowly and continuously enrich the model, okay? And this is a paper from 2018 that uses more standard traditional computer vision techniques. But more and more people have been looking at increasing the robustness of those algorithms. The first thing people are looked at is try to embed typology detection and modeling the constraints of typology, that a wall should be connected to a floor and ceiling, in order to ensure that not only the models actually look good, but they're actually semantically logical. And they also improve the performance overall of the modeling. Now, these things have been used often using hard-coded rules, but there's certainly some work. I think we saw in the presentation from Raphael Sachs on the first day, some work about learning typologies in buildings using machine learning. And this could certainly feed into models like that. And over the years, we've continued improving things. And now this is just to show you the result of a paper from last year by Bosche and Vergauwen that shows you, how these kind of algorithms apply to large-scale point clouds acquired not of empty environments, but actually inhabited and occupied environments. And the performance is really increasing very fast. Certainly not perfect. Lots of improvement can be made, but we're really improving. And there's still some new ideas that are coming out. For example, we have this paper from Iro, who's now in ETH, and her colleagues, who's been using semantic modeling to detect different types of components within spaces, sorry, that's what I meant. We have also some recent work that has been done in using instance segmentation to segment the point cloud, but also model them and semantically enrich the models at the same time. So there is some really interesting new ideas that are all machine learning, or at least when I mean machine learning, I mean supervised learning based techniques that are, I think, improving the state of the art and will trickle down and continue to improve what we can achieve. Just a shout out for ourselves. We've been doing some similar work. For example, what we do in the Beamer project is we do some Scan-to-BIM on the structural side, just like many people have done, finding walls, finding windows, finding ceilings, you name it, but also try to continue the enrichment with mechanical, electrical, and plumbing equipment. So here, using imagery from photogrammetric reconstruction, we train models to detect different type of components. And once we have these detections, we can actually reproject them into the model and enrich the models further. And that can be quite useful for doing things like energy analysis, but also if you have to plan renovations, you would need to know where some electrical component or mechanical components are located. So, this is some work we do, and there are other people actually I've seen who do similar things. I'll now talk about the second, and that'll be my last topic, I think, which is scan versus BIM. So what's the difference between scan-to-BIM and scan versus BIM? So in the context of scan versus BIM, we believe that we already have a semantically rich model of the asset. And this is increasingly true for all the new buildings that we are building. We don't just generate the traditional old 2D drawings. We actually now generate those semantically rich models. And we can use the 3D imaging technologies to acquire data. For example, here we have a laser scan on site. And we can use the prior of the design model, the BIM model, to process that data and infer various types of information. So I show at the bottom, if we put the two models in the same coordinate system, then you can start making inferences or help in the processing of the point cloud, which, in the construction domain, one of the big challenges of this type of data is that there's so much noise everywhere, so many temporary stuff here and there. You can see in the image here, this is during structural construction. There's a lot of form work, there's safety equipment, there's shoring once it's finished, there is the crane, there's so much stuff everywhere. So, if you were to process this without any prior, well, you might be able to to some extent, but I think, having the prior of the BIM model is something you must rely on. Or it would be, in a way, a bit stupid not to make use of it. Now, I personally did some work in that area for quite a while, and I continue to do some work at the moment. But I think some of the interesting work that has been done is actually by you, Andre, and your colleagues in Munich, where you were using this to try to track progress in construction. And so the typical way to approach the problem is to say, well, you can look if a point is next to a component, next to an object in the BIM model. And if you can find many of those points, then you can probably infer that the object has been built and is there, right? So this is a traditional approach that every one of us has been using. The only issue is that it only gets you so far. You can easily get confused, and you need to improve the robustness. So you can use different types of AI techniques for this. Here in their paper, they propose two things, actually. One is to do some color analysis, because often these point clouds, they come with color. And for example, they were showing here in the image how you could distinguish formwork from finished concrete, right? Formworks tend to look different. In fact, they are often very colorful. And so, it's a basic idea, but it's actually quite good, especially because if you look at the surface of formwork and the surface of the finished column, they are very close to each other. So distinguishing the two without using additional information than proximity might be difficult, especially if you base your analysis on drone data, for example. So using color here is a great idea, and they even push the idea further in a way, in a logical way. They train some CNN network to recognize formwork. It's not good enough to just, well, it's interesting to say, let's look at color, but the logical thing now is to say, actually, formwork are visually quite distinctive. So surely we can train an RCNN to detect them, or other type of networks. And yes, it actually works quite well. And they were able to show that they can use these detections to further improve their performance. So I think that was me. I think I'm bang on time. I would like to thank you very much. And I would also like to thank the rest of my team at Enbra who've been contributing to this work, Enrique and Martin and Dibia and Boan and everybody. Thank you very much if you are following me today. Thank you.